All right, everybody, welcome back. Today we're going to take a journey through the most important concepts and formulas that we covered this quarter. You can think of this as like a review for a final exam for the course. Generally, I hope to emphasize the topics and concepts that I think are the most important and will likely show up on a final exam. Hopefully in about a normal sort of lecture time period, we'll make it through all of the content, all the major sections of the course, and be able to uncover those highlights. Okay, so we started the course by doing a review of thermodynamics, so we will go ahead and start there. So we talked about some of the fundamental aspects of thermodynamics. This is stuff that, in essence, you should have came to the class with, but often is forgotten after a couple of years of not studying it. We had the first and second laws, which we brought together in this sort of universal universal total differential equation. All right. We also had enthalpy, which is defined as the internal energy plus the pressure times the volume. Okay. And then that would allow us to have a different expression for this du equation, this first law equation, where we can write it in terms of the enthalpy, where it's TdS plus VdP. Okay, we also discussed specific heat. Where the specific heat at constant volume is the partial derivative of U with respect to T at constant volume. For a monatomic gas, this is equal to 3/2 R. Okay, and then we also have Cp, which is dH dt at constant pressure, and that's equal to 5/2 R for a monatomic ideal gas. Monatomic as well, not just ideal. We define the ratio of specific heats, gamma, which is equal to Cp over Cv. Right? And then we I should actually also take a moment to define what we mean by an ideal or a perfect gas. What we mean is a infinitesimal non-interacting bunch of particles. Okay, just to kind of go back to make sure we understand what that definition is, what relevant assumptions we're always making when we use this model. We also discussed the polytropic process. This is where P times V raised to the power n is equal to a constant. Okay, and that's some specific values of n that correspond to processes that we're familiar with. N being equal to 1 is an isothermal process. N being equal to infinity is what we would call isochoric, or constant volume. N being equal to 0 is isobaric. And then N being equal to gamma is isentropic. Okay, so there's the polytropic process. Let's do our standard highlighting. Just keep things consistent here. And that kind of brings us through our thermodynamics fundamentals. The next thing that we talked about was the Reynolds Transport Theorem. theorem, which in its most general form can be written the following way: dn dt being equal to the partial derivative with respect to time, or the local derivative, of the integral over the control volume of eta times rho dv. Okay, and then we also have the integral over the surface, the control surface, the boundary of the control volume of eta rho times v, and we'll call this VCS because it's the velocity relative to the control surface, dot product with n hat. Okay, and when we're talking about mass, we have that eta is equal to 1, and also just from our knowledge of physics, we know that in that case dn dt, which would be equal to dm dt, is equal to 0. So we don't have mass production or destruction in non-relativistic systems. Then we have eta equal to velocity as measured relative to the reference frame, if we're talking about momentum. And in that case, dn dt becomes a vector quantity, dp dt, which we know from physics to be equal to the sum of forces active on the system. And then we have, if we're talking about energy, then of course eta is equal to E. And then dn dt becomes dE dt, which from the first law we can write as dq dt minus dw dt. Okay. And that's, and these heat and work values, we're talking about across the control mass boundaries for those guys. Work entering and exiting, and work and heat entering and exiting the system. Okay. So a lot of the work with the Reynolds Transport Theorem is choosing a good control surface and control volume and making sure you do your accounting correctly. But in terms of formulae, that's really all that there is to talk about. The next sort of main important topic that we discussed was this idea of the stagnation reference state. Which we can remember that the definition of this is that it is the state that exists when the fluid is brought to V equals 0 and Z equals 0, in other words, zero potential, isentropically. So no heat or losses. Okay, and then by using that definition, we arrived at the definition for the total enthalpy, which we can write as H plus a V squared over 2 plus GZ. And for gases, we usually just take GZ to be equal to 0. Okay, because the mass is so small, not really affected by gravity all that much. Then we have this following fact that for a system with both work and heat being equal to 0, we know that HT is equal to constant. It doesn't change. And we also know, crucially, that PT2 over PT1 is equal to e to the minus delta S over R. Okay, so if there are any losses in such a system, like across a shock, for example, you can calculate the drop in stagnation pressure across that non-ideal process using this function right here. Okay. Once we got through the stagnation reference, we talked about the sonic speed and the Mach number. So we derived the sonic speed itself to be equal to the partial derivative of pressure with respect to density at constant entropy, and that would be equal to gamma RT, right, for a perfect gas. And then we defined the Mach number m as V over A. And then we had this sort of point in the lectures where we talked about the Mach cone, right, where if an object is moving, you have along this sort of dotted line here, you have this zone of action in here, zone of action, and a zone of silence outside. And this angle here was mu, called the Mach angle. And sine of mu was equal to 1 over m. Okay, and this is where we kind of got our first notion of causality and how objects can be moving so fast that objects upstream of those of that object has no idea that it's coming, for example. Okay. From a fluid dynamics point of view, at least, which is where we end up with shocks. Before we got to shocks, though, we talked about how the stagnation reference state interacted with these sort of sonic velocities in the Mach number. For example, we wrote the stagnation enthalpy in terms of the by just doing some substitutions here. For example, we were able to write the stagnation enthalpy in terms of the Mach number, which we can then, because we're always assuming it's perfect gas and H is equal to CPT, we're able to say the stagnation temperature is equal to T times 1 plus gamma minus 1 over 2 m squared. So we have the stagnation temperature in terms of the Mach number, and the same thing for stagnation pressure, where PT is equal to P times 1 plus gamma minus 1 over 2 m squared raised to the power of gamma over gamma minus 1. The sort of all-important relationship between the static and stagnation pressures that we've seen many, many times in this class. Once we came up with those relationships, we moved on to talk about variable area flow. Right. And this is really just summarized by these two tables, where when dA is less than 0, if the Mach number is less than 1 and the Mach number being greater than 1, so this is like the case where the duct is getting smaller, right? And we talk about what happens to rho, P, and V. And in general, we see this strange behavior where when the Mach number is greater than 1, things are kind of the opposite of what we would expect. Thinking about something like Venturi flow, where things speed up when you send it through a smaller surface area for subsonic flows. But when your flow is compressible, the opposite is true. So this is for dA greater than 0. Same deal. Mach number subsonic and then supersonic. And then we look at what P rho V. This is, of course, an expanding duct. And we can see the Mach number is increasing, or sorry, the density is increasing. The pressure is increasing and the velocity is going down for an expanding flow, and then vice versa for the supersonic case. The velocity really is the thing that is different from what you would expect from your fluid mechanics course. And then this allowed us to jump into nozzles and diffusers. Diffusers. So we talked about the kind of the definition, right, where this thing that I'm drawing here, where the flow is moving this way, where the Mach number being greater than 1 is a nozzle, which converts H to kinetic energy, but that same configuration where the Mach number is less than 1 is a diffuser, which converts kinetic energy to enthalpy, right? So that was the definition of the nozzle and diffuser. And then we talked about choking, which is this whole discussion about causality, right? So we had this case where we had a small driving pressure gradient, and in this converging nozzle, in this converging nozzle, you had a subsonic flow at the beginning and still subsonic at the throat. Then we make delta P big enough to choke the flow, or to bring the flow to Mach number equal to 1, right? Just at that cutoff point. And then we make a really, really big delta P. And this guy, or in this case, we still can't increase our Mach number any further beyond m equal 1, because we're blind beyond the throat due to causality. Okay, and then the question is, okay, P huge, how huge? Well, remember the criterion for choking is that the total pressure upstream of the receiver has to be at least 1.893 times the receiver pressure, static pressure. Okay, and that number you get from plugging in the m equals 1 into this relationship between the static and total pressure. Okay, for air, for gamma equals 1.4. This sort of showed us, since we can't accelerate the flow beyond m equals 1, it made us think about or come up with the idea of the converging diverging nozzle, or the de Laval nozzle, where you have, that's terrible, you have this sort of geometry, where you start with subsonic flow, you reach sonic flow at the throat, and then that second diverging portion continues to operate as a nozzle and accelerates the flow even further. But there's also the converging diverging diffuser, right, that we have at the sort of the front end of our propulsion systems, where we have a supersonic flow coming in, and then we still reach that choked condition, but then we're able to continue to decelerate the flow through the diverging section of the diffuser, right? So those are the kind of the important paradigms and topics to think about for nozzles and diffusers. Normally, in a in-person lecture, we would stop and maybe discuss whatever topics were people are struggling with. But since this is just an online version, I'm just going to kind of power through. The next thing that we talked about was these equations called the working equations, as well as the sonic reference. That star reference state, right? So we have all of these things like T2 over T1, for example, or the pressure between two points, or the area even between 2 points, right? These are all sort of functions of the Mach number at station 1, the Mach number at station 2, gamma, and the change in entropy. In particular, these two guys are a function of that, right? Not the temperature, actually. These things are not tabulated, right? These are just functions that you would plug in values to, right? But then there's this idea of the sonic reference state, which we call the star state, say. So this is the state reached by isentropically adjusting to m equal 1, right? So here you have A2 star over A1 star. We found that this was actually equal to e to the delta s over r, which is also equal to PT1 over PT2. And then we found this important closure equation, PT1 A1 star is equal to PT2 A2 star. Okay, so that was one result that we found when we defined the sonic state. And then we have the isentropic relations. In this case, specifically for A over A star, with reference to the sonic state. So A over A star, as we defined it in class, was 1 over m times this quantity 1 plus gamma minus 1 over 2 m squared over gamma plus 1 over 2. All of that raised to the power gamma plus 1 over twice the quantity gamma minus 1. So that thing is actually 1 over what we could call like F Cantwell of m, okay, that we've been talking about in the propulsion section of the course. And this is sort of tabulated on Appendix G. Okay, so that's that all-important area Mach relation. Okay. The next topic that we went into was standing normal shocks. So this is where we showed that M2, the Mach number downstream of the shock, the ratio of components across the shock, T2 over T1, PT2 over PT1, the entropy change, S12, these are all functions of F, of just the upstream Mach number in gamma. They're tabulated in Appendix H of the textbook, the Zucker and Biblar's textbook. Keep in mind that these two guys are essentially equivalent, related by this relationship here that I'm going to underline in red. All right. So this is where we started talking about a little bit more about nozzle operation with these pressure curves, right? So if we have This is that third critical operation. We can also have a shock here, and that would be our second critical. This is a distance, and this is pressure. Then you could have some shocks inside the inlet. I go here. Or you have that first critical operation too, which is just like the limit of Venturi flow. Okay, this is the quintessential plot that tells you about nozzle operation. Okay, and then just a couple little notes. This is where overexpanded flow phenomena occur, like oblique shocks and expansion waves, starting with oblique shocks from the nozzle, and then this is where you have underexpanded flow. In which case you have Prandtl Meyer expansions right at the edge of the nozzle. That's what happens first. Okay, and then this was at a point where we're like, okay, now we have these shock structures on the outside of our nozzle that we need to account for and describe, and so it's time to talk about oblique shocks and expansion mechanisms. But first, we talked about oblique shocks. So we drew this diagram over and over again, where you have some velocity coming in this way, v1, and a shock kind of at an angle there. We have a component of that velocity that's parallel to that shock. We call that v parallel. And then we have a perpendicular component, which is v1 perpendicular. Okay, at right angle there. And then coming out, we have a smaller v2 perp, right? But v parallel is the same size, v parallel, which causes our overall direction to change here. So that angle there, I'll label it with a different color, is delta, which we call the deflection angle. Okay, this is V2, the overall V2. This angle is the shock angle. Sorry, is the shock angle theta. All these angles are measured relative to the incoming flow direction, of course. And then there's this other angle here, which is important to know off the top of your head, which is just theta minus delta. Okay, and some important relations. We know that m perp 1 is equal to m1 sine theta, which tells us that the minimum shock angle is equal to mu, right? We also have v parallel 1 is always equal to v parallel 2. So it leads to this behavior. But an important thing to remember is that m parallel 1 is not equal to m parallel 2. Okay? Because the temperature changes across the shock. Static temperature, that is. All right, we derived an expression for the deflection angle in terms of the shock angle and the upstream Mach number. So we have the tangent of delta being equal to m1 squared sine squared theta minus 1 divided by m1 squared times gamma plus cosine 2 theta plus 2. Okay, and this thing is tabulated or plotted in Appendix D. And then the important thing to remember about oblique shocks is that they occur to satisfy pressure and flow direction boundary conditions. Okay, so remember that. That's what gives rise to these phenomena. Okay, so now, excuse me, apologies for the yawning. Now let's talk about Prandtl Meyer, which is the next topic that we discussed. Because we had that compression mechanism for under-expanded flow, but then we ran into this point where we needed some sort of expansion mechanism, right? So the typical setup that allowed us to derive this, the mathematics for this phenomenon, was this sort of gradually changing direction thing here, where you have some sort of initial m, and you know that your final Mach number is parallel to the wall up there, but along the way you have to go through this fan of compression processes that coalesce to form a oblique shock with a shock angle equal to what you would need to satisfy that boundary condition. And we know that MF is less than MI in this case. The overall deflection is delta, okay? And then there's, so those are Prandtl Meyer compressions. That are coalescing to an oblique shock. And then we had let me just kind of add some texture here to show where the wall is. And then we had the expansion fan, which is when you turn, let's say down, turn off normal into a region of low pressure. So then the initial MI comes in, you know, the final Mach number, which will be greater than MI in this case, has to be parallel to the boundary, the solid boundary there. And we have our set of expansion waves, which kind of look like this. It's a fan of expansion waves. Okay. Interesting thing to keep in mind is that the angle between the first expansion wave and the flow direction is the Mach number, or sorry, is the Mach angle of the initial flow. And then the Mach angle of the final flow is less than the Mach number of the initial flow, just because the Mach angle is less than the Mach angle of the initial flow, because the Mach angle is equal to the sine of the inverse of the Mach number. Okay. So this is a PM expansion fan that we've drawn here. Then we had this tabulated function nu, which is the Prandtl Meyer function, which is a function of m, the upstream Mach number, and gamma. This is tabulated in Appendix G. And we have sort of the picture that I would draw for this is we have, you know, an m naught, which is equal to 1 and has some sort of nu naught associated with it. And then we have an m1, which is greater than 1. Sort of two angles to draw here, right? So this delta nu, sorry. We have delta nu here, and we have a larger angle, which is nu 2. Okay, and then we have an m2, which is greater than m1. So if you find the nu that's associated with the final Mach number, you'll get this angle between the sort of Mach equals 0 flow and the final flow, and you have the difference between those two is the is nu 1. So delta nu is equal to nu 2 minus nu 1. Okay? And then just remember that for compressions, use negative values of nu. Okay, these are all expanded, so it would be positive. And then once we got through talking to these, that explained the structures of Mach diamonds. Right, where we have, you know, a nozzle finishing here, and we have oblique shocks, followed by Prandtl Meyer expansions, which coalesce into more shocks and so on. Everything continues. Actually, those actually just continue. Eventually turn. So, and you get that Mach diamond structure. Apologies for the messiness, right? We also talked about supersonic airfoils, and we saw how, because we don't want the shocks to become attached and cause large losses, you end up with these sharp leading edges for these airfoil devices. And depending on your angle of attack, you can have different sort of structures, open flow structures, expansion waves, or oblique shocks, right? Okay, so once we got done with external flows, then we kind of went back into the channel, and the first thing that we talked about in that context was Fanno Flow. Which is flow with friction, right? This is you know, A being constant, but some sort of force of friction is present, right? And then because A was constant, when we did mass conservation, the A's drop out, and you just end up that with rho v equal to g. This new quantity, the mass velocity, is equal to a constant. And using that fact, we were able to draw what are called Fanno lines. So we know that since it's adiabatic, that ht is constant as well. So one way of writing that is that ht which is equal to h plus g squared v squared over 2 is equal to a constant. We can plot those lines on an HS diagram. HS, and we had these sort of lines show up, so we can plot the HT on the thing here, and then we had these lines where, right, and then the limiting point at maximum entropy was our star F state. Okay, and G increases in this way. And then we knew that the branch above the limiting point was subsonic, and the branch below is supersonic. And we were able to come up with a table kind of like what we did with variable area flow, where we have a property and then the upper and lower branches. So, you know, things like enthalpy, density, velocity, pressure, and stagnation pressure vary in the following way: down, down, up. Well, this little up here in the velocity row was to me one of the more baffling things about Fanno Flow, that you have increase in flow velocity as you move down the channel. But it is true, since you're pulling energy, you're losing pressure head. and the mass velocity is constant, so it causes V to go up. And then you get the opposite of everything except for the stagnation pressure for the lower branch. Excuse me. The one important, when we went through the working equations for Fanno Flow, the most important one was this distance equation, right? Which itself was some function of m1, m2, gamma, okay, which allows you to find m2 given your initial Mach number and how long the channel is. And that sort of brought us to that star F reference. So you're adjusting the flow to m equals 1, this time along the Fanno line. Right? And so we drew, a couple of diagrams, like we would look at a Fanno line on a TS diagram. It would be like this, and we'd look at this, and we'd look at a pipe that has some sort of actual extent, and then there's some sort of like hypothetical extension of that pipe to a certain point where you hit m star f equal 1. And this distance is x star f. Then we have x2 here and x1. Okay. And the way we can draw that is 1 being here, 2 being here. And this thing is both state 1 star f and state 2 star f. It's the same for all states on the same Fanno line. And then this allowed us to kind of define another set of like parameters that are very much like the isentropic or sonic tables, or the isentropic tables, where you can have property ratios like the following, which allow you to solve various problems that are all a function of just the upstream Mach number and gamma. And then we have this very important one, which is x star f minus x, which is equal to L max, which becomes very important for solving these Fanno Flow problems. We also briefly talked about shocks on Fanno lines. So if you start down here in the supersonic branch, and then you come here, the shock takes you up to the subsonic branch, and you can continue forward. The reason why it jumps that way is because it's jumping to a point of equivalent. I forget exactly what the quantity being conserved is, but it has to do with momentum conservation, which is not so simple because we have a force of friction present. Okay, so what that looks like is you have some Mach greater than 1, a shock, and then the Mach less than 1 in a Fanno flow. So this will be like state 1, 2, 3, and 4, and this is state 1, 2, 3, and 4. Okay. After Fanno Flow, we went on to Rayleigh Flow, which is very, very similar mathematically to Fanno Flow, just of course different physics. So this was also steady, dA being equal to 0. We also made this very important assumption that the change in entropy due to losses is much, much less than the change in entropy associated with the heat addition. Along with that assumption, we have steady 1D, dA equals 0, etc. Okay. bunch of different assumptions. This led to G being constant once again, because the area is constant. But importantly, TT is not constant. And this sort of is a major departure from all the other cases that we would talk about. A Rayleigh line, as a result of all of these assumptions, is defined by this P plus G squared times V equal constant equation, right? And importantly, that leads to the following TS diagram, where we have kind of shaped like this. Okay, and we get sort of two distinct points here. One, and here I'm actually going to move this down so I can draw the total enthalpy variation at the same time. So the total enthalpy has this behavior like this. So that's the limiting point. This is the supersonic branch is the one on the top. Supersonic, subsonic. This is subsonic. And this is supersonic. And the star R reference state is here. This sort of like state 2, let's say, if we were starting here at 1. State 2 is the point of maximum temperature, but not the point not the limiting point, even though we're adding heat, right? The temperature will start to go down. The stagnation temperature will start to go down if you continue to add heat. No, sorry, not stagnation temperature. Stagnation temperature always goes up as you're adding heat. The actual static temperature goes down. Okay, then we have this, table that we continuously draw here, where we look at the way properties vary on the upper and lower branches. Right, so things like enthalpy, density, velocity, pressure, total pressure. The enthalpy is unique in that it goes up and down on the upper branch, but on the lower branch it just goes down. The density goes down, of course. You add heat, then the opposite, the non-intuitive thing is happening on the lower branch, where the density is going up with additional heat. In general, this case follows the rule that you normally follow, where having a supersonic behavior flips things to unintuitive. That kind of works across the board for the Rayleigh line, or for Rayleigh flow, or Rayleigh flow, I should say. The working equations. These are the same as always. They're just property ratios. Property ratios that are some function of M1, M2, and gamma. Okay. The important thing with the Rayleigh flow is that the way you close the system is with Q being equal to Cp times Tt2 minus Tt1. Okay, so the total amount of heat that's added. That allows you to close the system, because you can calculate the downstream stagnation temperature. Once you have that one downstream property, you can kind of get the rest. Okay, the star R reference, same definition that we've been using, like for Fanno Flow, for example. The star R reference is when you adjust to Mach number equal to 1 along a Rayleigh line. Right. And then for the shocks, the only thing to kind of remember is that you have to, in this case, hop to the same stagnation enthalpy, because that's not conserved in Rayleigh flow, and that is conserved across a shock. Okay. And you can go back and look at what that TS diagram looks like. I won't reproduce it here. So, and then our last topic, broadly, was propulsion. And we covered a lot of ground. The first thing that we started off with was kind of defining some key metrics, things like efficiencies, right? We started with thermodynamic efficiencies, like the Brayton efficiency. This is equal to 1 minus T naught over T1, right? We talked about the Brayton cycle itself, which follows this sort of ds equals 0, the dp equals 0, ds equals 0, and then a dp equals 0 process, and then it continues the cycle. The heat addition comes in, and the heat extraction or rejection comes out in the isobaric processes. Okay, important to understand what the Brayton cycle is, since a lot of these propulsion systems use that. We define the propulsive efficiency as the thrust times the cruising velocity divided by m dot a times ve squared over 2 minus v naught squared over 2 plus m dot f ve squared over 2, or in other words, the change in kinetic energy of the propellants. So the total jet power divided by the change in kinetic energy of the propellant. This can be simplified to 2 v naught over v naught plus ve in the case where f is much smaller than 1 and you're a perfectly expanded nozzle. Okay, we talked about a general definition for thermal efficiency, where we can just write it as 1 minus the Q rejected over Q inputted. That allowed us to kind of talk about the energy transfer within our engines a little bit more intelligently. We had this overall efficiency, which was the overall thrust power divided by m dot f. HF, or the total amount of energy that's being inputted by combustion. This can be written in a non-dimensional way as 1 over, or in terms of non-dimensional quantities, I should say, as gamma minus 1 over gamma times 1 over f times 1 over tau f times T over P naught A naught, or your non-dimensionalized thrust. Our expression for thrust in dimensional form was m dot A times VE minus V naught plus m dot F VE plus PE minus P naught times AE. And then we non-dimensionalize this expression in the following way, where you end up with gamma m naught squared times the quantity 1 plus F times VE over V naught minus 1 plus AE over A naught times the quantity PE over P naught minus 1. Okay, that was a non-dimensionalized term. And then if you have a turbofan engine, you have to make sure you add those relevant terms to that thrust equation. Okay, and then this is where we kind of jumped in and we analyzed the 3 different propulsion systems that we went through. So the first one that we looked at was the simplest was the ramjet, where you just have you don't have any sort of active components in the engine. You just have a diffuser that slows down the flow, and then a burner, and then a nozzle that accelerates it. Right. We also had the turbojet for cases where you're not moving fast enough to compress the flow just using a diffuser. I'll make this a tad longer than the ramjet so I can make sure I have enough room to draw the internal structure. So we have our diffuser, and then we have a compressor before the burner, which is connected via a shaft to the turbine, right? And then the most complex one that we went over was the turbofan, which puts a bypass flow around the turbojet core and adds a fan. Can draw it this way if you're inclined to. We have a shaft now connecting both the fan and the compressor to the turbine. And then we have this bypass mass flow in the fan, and then the core flow here. Okay. So a couple of things that we talked about when we analyzed these engines. We know that the ramjet is sort of good for a Mach number of about 3.5. The turbojet is better for a Mach number, less than and equal to 1. It's kind of around the just subsonic regime. And then this is better for even lower Mach number, so Mach number less than 1. This is where, this is what commercial airliners use. Okay. This is bad at both high and low Mach. At high Mach, you might as well use a ramjet, not have all the compressor, but you do need more compression. So the compressor needs to be doing more work at low Mach number. Was one of our key contributing factors. And then with the turbofan, we had these new definitions that I want to make sure I write down, which is this bypass fraction. Bypass. I think beta is the bypass fraction, right? M dot fan over M dot core, and then B was the bypass ratio, which is M dot fan over the total airflow M dot core plus M dot fan. Okay, the ideal efficiency that we got for the ramjet was 1 minus T naught over TT0. Then eta ideal for the turbojet was 1 minus T naught over TT3. It's having to do with that compressor. And then the eta ideal for the turbofan was actually the same as the turbojet, and that was because the fan was adiabatic. All right. Okay. So some unifying propulsion ideas. Right. The first thing is this mass flow rate expression in terms of the stagnation quantities, which is has all this complicated expression in terms of gamma out front, but in practice, since we assume that the gas is perfect, this sort of cancels out anyways. What really matters is the business end here, which is that PT times A over gamma R, but really just a square root of TT times F. And again, I'll put a subscript on it. I really should have been doing this the whole time, but an FC of M, denoting that that's that Cantwell definition of that Cantwell area Mach relation. So the inverse of what we had in Zucker and Buchlar's. So this is just, relating properties across components. But it's also useful for, looking at limiting cases. So like you did this in your homework, but you can look at the case where you're right up in the edge of something choking or unchoking, And you can see that, if you were to increase the amount of heat that you had added, so therefore increasing the stagnation temperature, for example, that would require a stagnation pressure drop. And if there's no other mechanism to introduce that, or if you're holding the turbine or something constant, then you know that you're going to have some sort of shock appear, for example, that can provide that stagnation pressure drop. Okay. One thing to remember, just as a note, remember, A4 star, where F of M4 star is equal to 1. So that's an important station whenever you're talking about station 4. A4 star is talking about where the flow is choked on that first stator of the turbine blades. Okay, so another thing to keep in mind with propulsion are these non-ideal factors. So the way that we keep in mind, factor these into our calculations is with these polytropic efficiencies, for example. So, as an example, PT3 over PT2, they're related to each other according to TT3 over TT2. Normally it would just be gamma over gamma minus 1, but in this case it's gamma times eta PC over gamma minus 1. Okay, and then don't forget that the pressure ratio across the turbine has because of the way that the polytropic efficiency of expansion is defined, that polytropic efficiency ends up in the denominator where you have gamma over the quantity gamma minus 1 times eta PE. Okay, that's a common mistake. And then of course isentropic operation has both of these polytropic efficiencies equal to 1. And then one more important idea besides keeping in mind this, relating these different stations using the mass flow rates, you also want to be able to do energy balances between components. Right? So, for the turbofan, if you're doing the energy balance across the shaft, it looks like m dot core plus m dot f times HT4 minus HT5. In other words, the energy pulled out of the flow by the turbine. That would be equal to m dot core times HT3 minus HT2. This is the energy change across the compressor, the energy injected into the flow by the compressor. And then you have m dot fan HT13, let me make that a little bit clearer, HT13 minus HT2. This is the energy injected into the flow by the fan. Okay, so that's the energy balance across the turbofan shaft. There's also the burner energy balance where you have m dot A plus m dot F times HT4 is equal to m dot A HT3 plus m dot F HF. Right. This one in particular is useful for finding the F, which is equal to m dot F over m dot A total. Right. So that's something to keep in mind for that burner thing. Okay. So that actually brings us to the end of the class. I don't know how long this has been, but it's a little surprising that you can fit basically everything into this much time, but of course we didn't go through too much detail. But if you have any questions, please feel free to reach out. I think that I'm hopeful that the course was both interesting and that it will be useful to you, that you find it valuable. If you have any feedback that you could give, I'm happy to receive it. As far as these lectures, these online lectures go, I know they're definitely not the best. I will be making major improvements to these down the line once I've had a few iterations of teaching the course, know what topics to take in and take out, what sort of tweaks can be made to the lectures. I'll definitely be doing that. But for the time being, since I wanted to have a little bit more in-class practice and also have lecture materials available to students on demand, I wanted to go ahead and record these just right out, as soon as possible. And then, a couple years down the line, a few years down the line, we can put a better version of these online. But the reduced quality that they may have, I hope that they've been enjoyable and useful. And like I said, please let me know if you have any feedback. I'll be happy to accept it. And otherwise, if you're just watching online, thanks for watching. Hope you can find other videos of mine to enjoy. If you are in the class getting ready for the exam, good luck. I hope it's both challenging and fun for you. Although the second one is definitely more hopeful. But yeah, anyways, have a great one, everybody, and I'll see you next time.